on now. Good evening, everyone, and welcome to our CAWASA webinar series. This is number 19. We had a break last week because of the CWWA annual conference, which went very well via WOVA. It was a virtual conference, good participation. It continued today with the high-level forum for ministers of water. That was yesterday and today. And wastewater and waste high-level forum will take place next week. But this afternoon, we are going to have a presentation by Ms. Michelle Shah on pond production for water storage, conservation, and flood alleviation. Ms. Shah has been following our webinar series and has been generous enough to become a presenter this afternoon. She holds an M.Sc degree in Water and Wastewater Services Management from the Department of Civil and Environmental Engineering at the University of the West Indies, St. Augustine campus, and has been employed as an agricultural engineer for the past 26 years with the engineering division of the Ministry of Agriculture, Land and Fisheries of Trinidad and Tobago. Her duties and responsibilities as an agricultural engineer encompass providing technical advice to farmers and the design and implementation of agricultural projects involving infrastructural development, construction and rehabilitation of roads and culverts and bridges, development of water conservation, storage and management systems, wastewater management systems, operations and emergency response, equipment and machinery. Ms. Shah was awarded a scholarship in 2018 by the OAS through the Government of Chile Scholarship and Training Project for CARICOM countries to pursue an on-site certificate course in water management and irrigation technologies for smallholder development and irrigated agriculture in times of climate change for CARICOM countries, held in cooperation with the OAS program. That was at the Agriculture, Environment and Water Training Center of the Galilee International Management Institute of Israel. Ms. Shah represented the Ministry of Agriculture, Land and Fisheries in 2019, being part of a team that attended the Ministry of Agriculture and Rural Development of Colombia training program in food security and nutrition projects via invitation extended by the Ministry of Foreign Affairs, Department of International Cooperation of Colombia. She presented a research paper titled Pesticide Administration Strategies for Hazard and Risk Management on Farms in Trinidad and Tobago, a case study in the Orange Grove Estate, Tecarigua, at the Caribbean Water and Wastewater Association 27th Annual Conference and Exhibition held in October 2018 at Montego Bay Resort, Jamaica, and which was published in the association's annual magazine. Her skills and knowledge gained through years of experience in providing engineering solutions ensures that she sustains her responsibility to maintain the highest standards of professionalism through all her projects. I now invite Ms. Shah to begin her presentation. The floor is yours, Ms. Shah.
Thank you, Mr. Jean. I warmly welcome you to this online webinar series number 19, covering water operators, partnerships, Caribbean utilities joining forces to fight climate change, organized by CAWASA, which is an association of water utilities committed to the efficient management of the region's water resources and applying our collective experiences to solving water sector problems. My name is Michelle Shah, and I am an agricultural engineer too, and I am employed at the Ministry of Agriculture, Land and Fisheries in Trinidad and Tobago. During these unprecedented times caused by COVID-19, we and all at the Ministry of Agriculture are doubling our efforts in working with all the divisions for harnessing digital technologies in bringing its training and development capacity initiatives to a much wider listening and viewing audience, and to benefit from training opportunities such as this one held today on pond construction. Or allow me to thank Mr. Ignatius G., Executive Director of CAWASA, for giving me this opportunity to share this training information to you, the participants, via this initiative, and in making this online course freely available to you and to hundreds of other stakeholders throughout the Caribbean who will also benefit from this course. The course has been designed to provide you with maximum flexibility to learning access anytime via Zoom recording and slides which will be made available to you. Please be informed that questions may be asked after the presentations and ideas can be shared via the chat box both during and after the presentation. I encourage all of you to take full advantage of this online training material which is being made available to you and which will be of practical use for you in the future. Once again, welcome to you all, and I wish you a very fruitful learning journey. I thank you.
Yeah, well, you can begin to share your screen. Yeah.
Okay.
And your audio as well, remember.
Okay. Is everyone hearing?
Oh, you have a problem. Your screen is still showing your folders.
Okay. Well, I thought it had okay, I'll have to try and check. All right, I have to check and see why this is happening.
Stop sharing and then share again, and then just open the the folder that you want to go to.
Okay, I stopped sharing and
right, good. Then go to your folder and open what you want to share, and then begin sharing.
Right. Right. And where do I start sharing now?
When you go to start sharing, you should see a number of files and folders you probably opened already. So if you have already opened the presentation, just look for it in there and then just click on it.
All right. I had already clicked on the folder, but
well, not the folder, the file itself,
yeah,
so the presentation file
because
itself.
I'm seeing it on my screen. You know, I'm seeing the presentation on the screen, so it's just a matter of I'll have to
In
go
the
back.
presentation, yeah. Now you then share the screen. Find the presentation and share the screen.
Yeah. Okay, I'm on the full screen and I'm going to share it. Right. All right, I'm now seeing what I'm looking for.
Okay, we got you.
You're seeing it?
Yeah, you just gotta make it wider.
I'm open it now. Yeah, right. Is that the full screen?
Yeah, go ahead.
Okay.
Yeah.
All right. Great. Right. Sorry.
Your audio might be a problem. We're not hearing the audio. Did you share the audio?
Well, I had to. I was looking for the section that had the little square on the left side. The square that shares the audio. I'm not.
You're probably.
Okay, I'll have to start from the beginning again.
Yeah, you have to go start from the beginning.
And then share sound, right? That was what I had to do. Okay, so right, so I'll continue from where I had stopped just now. Right, so you all can go, it can continue now, right? The costing section, we start with the cost for a 2-acre plot of a pond built on a 2-acre plot. Right, so when you're constructing ponds on 2-acre plots, we always know that it must take up at least minimal 15% of the land, because we don't want to use up the land where the crop is not being used for the crop. So we have to just use minimum amount of 15% of the land acreage. Okay, so let us now start with the cost of the water supply. Right, the water supply cost for 6,350 meter cube pond, because that is the capacity of a pond that is built for a 2-acre plot. I will show you later on in the calculation section how that 6,350 was obtained, right? So the water cost for a pond of that size, for if you have to obtain it from a water source, which in this case could be like truck-borne water or so, that is where there's no access to nearby channels or rainwater. There's no rainfall, for instance, or no groundwater available. You have to then obtain water via truck-borne water, and that costs you have 350 per meter cube. And for that capacity of pond, it will be 22,000. If the water now is obtained from rainfall or from rivers and underground sources, you only charge 10 cents per cubic meter. So therefore, the water supply would cost $635. Let us look at the cost now for equipment. The cost for equipment for construction of that capacity pond, which is a dimension of say 30 meters diameter by 5 meters depth, 5 meters, so that will be like 15 feet in depth. We have to rent an excavator. Some farmers will rent an excavator for say 10 days, and the cost should come up to 2,400 per day. So the cost for that pond construction, the equipment costs come up to $24,000. Using a backhoe now for 10 days, it will be a lot cheaper. You're getting $1,500 per day, and it comes up to $15,000. The more preferable equipment is really an excavator, because you have a longer reach where it will be able to dig the embankments, and the base of the pond will be would have a greater depth when you use excavators. So this is why excavators are more highly recommended for pond construction. Let's look at the cost for pumps now. In the construction of the pond, we would normally use a pump of 1.5 horsepower, and that will be for this particular pond size. Of course, there will be various size pumps for other size ponds. So we're just looking at this size in particular of a 1.5 horsepower, and the accessories for connection to the water to the pump to the actual pond. We would have to get accessories such as hoses, such as suction and discharge hoses. The discharge hoses are a lot more expensive than the suction hoses. And we have to purchase valves, filters, so that there will be no clogging of the pumps with sediments. And that total for the pump costs around 1,000 for this particular pump size. For other accessories are the PVC overflow and inlet pipes. We usually recommend 12-inch diameter, and say you get 4 lengths of PVC pipe, you get $1,000 per length, say, and you will get a total of 4 lengths amounting to $4,000. So this will be the overflow pipes for the outlet of the pond. That will be for prevention of overflow of the pond. You install the pipe in the embankment, and for the inlet pipe, you also put a pipe for intermediate transfer of water from the river to the pond. So that's what the purpose of the inlet pipe is. Right, so the next slide is the summary of the pond costing. So after that calculation, you will see a complete summary of what the total costs are. So if you look at rain-fed ponds, using the excavator amounts to $31,800 approximately for using an excavator. Using a backhoe, it comes up a lot cheaper, $23,000. And if the ponds are supplied by WASA via truck-borne water, you will have an excavator doing the works amounting to $56,000, which will be the highest cost in this case, $56,000, because the water is not rain-fed. And then using a backhoe, you get the total cost coming to $47,500, which is less than if you use an excavator. But the excavator is the more recommended equipment for use in pond construction. Right, so the 31,000 is the figure that we are most interested in for pond incentives, because this is where you are using rain-fed source and an excavator. So this is 31,000 is the figure we are most interested in. So that's the total for a pond on a 2-acre plot. Equipment costs now, these are just rates if the farmer has to be renting equipment. So we look at approximate rates per hour or per day. We have it per hour here for the excavator. We have it for a backhoe loader, a roller compactor, because the compactor is necessary for the embankment, compacting the embankment and the side slopes, as well as the base of the pond. We also have a crane. We have a cost for a crane, a crawler tractor, a dump truck, and a road grader. So each of these equipment costs, there's a mobilization cost, which is what takes up a high figure of 2,000 for the excavator. 2,100 is the mobilization cost per day. So this is what the figure. These are the figures you look at when you're estimating rates for rental of equipment. Okay. Now we reach module 4 now. Design criteria for ponds for drainage and irrigation. we look at the types of ponds before we look into what are the criteria for design. There are three basic types of ponds: sunken, diversion, and barrage ponds. We don't really consider barrage ponds in Trinidad because it is not feasible for the agriculture sector. So we really would be looking basically at the diversion pond first. This is basically what is used in Trinidad, the diversion pond, and in some cases sunken ponds, right? Because sunken ponds are where you have them in valleys and so on. So we would look at the other two, diversion and sunken ponds. The factors to consider for locating ponds now, the main factors are the topography, the proximity to the water source. Well, when I say topography, it means whether the land is flat or undulating, and it's highly recommended that ponds be dug on flat lands, preferably. But we allow slopes of at least 0.5% grade to 3% grade in slope. So, for instance, it would be grade meaning the vertical to horizontal half would be like 1 and 2, so 1 vertical, 2 horizontal. So these are the grades that would be recommended if a flat surface isn't available. Proximity to water source, it should be close enough to rivers and channels, but there is a limit though, because ponds should not be built too close to the river embankments. So I will give you those quantities later on. What are the limits that must not go above, that you can't go above in proximity to other channels and so. The soil type is another factor to consider. We have particular soil types we need to have for pond construction. Proximity to roadways, there are limits. Near ponds must be built to roadways and also to utility poles like electricity poles and so on. The proximity to buildings and other structures, there's a limit for those as well. Ease of access to the pond, the farmer must have ease of access. That is one criteria for being considered on the program. And the need for regular recharge of aquaculture ponds, that in this case, aquaculture ponds must be recharged because it is for livestock, so it is of necessity to have regular recharge in this case. Now, selection of pond type according to the slopes. These were, as I said before, these are the slopes, and preferably less than 5% is recommended. So, as I said, diversion and sunken ponds, these are the particular types we recommend, and it will slopes less than 5% are what we really recommend to the farmers. Right? These are definitions of what the sunken pond is. They are usually at levels below the level of the surrounding land. So as I said, it is found in valleys and so on, right? And they are directly fed by groundwater, rainfall, or surface runoff. Okay, and it is built either as a dugout pond because it is in an existing hollow, so it already exists in a hollow, as I said. So it just has to be excavated and dug out to increase the dimensions of the pond in this case. This is a diagram of what a sunken pond looks like. So you see the trapezoidal shape. It was dug out in that particular shape to get the side slopes. And in this case, they built up 2 embankments, the black area. They had to build upon a high embankment to try and store the water. So this is really done in sunken areas of land where there are depressions in the land, you know. So this is a type of pond that is built for irrigation purposes. The diversion pond, now this is what we recommend basically for flat land. This pond is fed indirectly by gravity or by pumping through a diversion canal, right? So it could be fed from spring water, underground water, or river channels. And it is done on flat ground, where you have to build 4 embankments so that there will be no overflow when the pond is full. And also the embankment will protect the pond if there is flooding in the area. So it is a double purpose. The embankment protects the water from flooding, and it protects from overflow of water from the pond onto the land. This is the diagram of the diversion pond, and in this case it is square in shape. It could have any shape, circular, square, or rectangular, and we have it being fed indirectly by this inlet pipe. As I said, inlet pipes feed indirectly from river channels, and this is how it's done, where water inlet is used to feed the pond. It is also fed by a pump, where the pump might be used to lift water from another water source by a nearby river, and the pump lifts the water, and it is used to fill the pond in this case. And you see the slope. This would be a 1 in 2 slope, or a 5 to 10% slope is allowed. The minimal of 5 to 10%. This is the recommended slope. That is 5 to 10%. This is the recommended slope that is used. These are advantages and disadvantages of the diversion and sunken pond. So we look at basically differences in cost. We look at the way the ponds are shaped, and so on. There's no need for embankments with the sunken pond because it is already in a depression. So this is an advantage. You don't need to build up the embankments as often as you would have for a diversion pond. So these are basic advantages and disadvantages of the 2 types of pond I just described. Right, module 5 now, the criteria for pond site selection. Well, I spoke a bit about being in the pond site being near to the source of water, away from roadsides, away from not too near to the river channels or utilities and so on. So pond sites now must be selected for most efficient and economic operation on farms with the following criteria: maximum surface runoff to be captured for storage without significant collection of silt and debris. So we consider surface runoff. Then minimum operational costs needed in pumping. So the operational costs using pumps, we try not to have pumps as that will increase the cost for filling the pond with water. So we recommend preferably rain-fed ponds and so on. But if it is necessary, we use pumps to get access of the water from rivers and so on. Minimal costs, so it is needed as in earthworks required. So the less amount of earthworks required, you get less capital costs. The minimum amount of drainage channels and so on that are needed within the plot. So you try to locate the pond you try to locate the pond near to where the crop is being cultivated, so you don't have as many lengths of pipes for the irrigation purposes to be you would have less amount of pipes needed for irrigation if you have the pond located near to the crop being cultivated. The soil quality determined by tests, as I spoke about earlier. The depth of the water table. So we try to build ponds, but we are not to go with where the water table has reached. We have to be above that water table, because it's not legal to have that to go in to reach the water table then. So it must be above the water table. The Water Resource Agency, they recommend not to interfere with the water table. So inlet and outlet structures, I described about that a little earlier. And access to utilities, I also described that earlier. We have infrastructure systems for this site. Well, as I spoke about the pumps and so on, you'll have a pumping system as seen in the picture that will fill the pond. And there are various capacities of pumps. There are farm reservoirs or communal storage ponds. These could be located on sites in close vicinity of the projects. So you'll have multiple stakeholders getting access to the water from a communal storage pond, right? So this is another type of pond where it's not for the individual farmer, it is used collectively by farmers, and in those cases farmers can do joint abstraction of license for water, and there are many locations in Trinidad where the farmers do this type of water storage by communal ponds. Earthen reticulation system within the site where the land is flat, clay soil type, high conveyance efficiency, right? So this is the earthen pond as I described, the basic diversion pond, and it is an earthen pond. Some people line the ponds, but we mostly just do earthen ponds in Trinidad. Because of the fact that the clay content is sufficient, it is at least 20% clay content, so that's what we recommend in the earthen type of pond, a clay content of 20%. These are just a few. Six, we have criteria now for design and associated pond structures. So we have efficient water control and distribution from the pond storage structure. So design of the pond for irrigation involves the design and assessment of the following: water availability, irrigation water requirement, and this is a vital aspect of the calculation of the pond design, the irrigation water requirement, which is based on cropping pattern and irrigation method. The design intake and conveyance canal, whether it's a pipe system or via canals which have been constructed on the surface. And then the design of pond capacity of the water storage reservoir, that is a criteria for the design of the pond. You need to determine the capacity that is required to hold. The application methods, and such as drip irrigation, sprinkler, and the surface water or free flooding method. Capacity of the pond shall be fixed on the basis of the source, water requirement, and pond operation rules. This is just summarizing what is said above there. Recommendations for embankment construction. Well, we have mostly the soil type is what is important. The height of the embankment refers to the height after settlement and compaction by a bulldozer, and whether it should be used for vehicular traffic, because sometimes if the top of the embankment is wide enough, there's use for vehicular access for vehicular traffic where it is a wide embankment in those cases. Right, the dimensions of the embankment are given in this table. So where we look at pond sizes of this square meter from 200 going to 400 to 1,000 square meters, we have recommended embankment slopes. So mostly recommended is 1 and 2 slope, and that would be for ponds which have less clay. If it has more clay in it, you can use slopes of 1 and 3. So the clay content determines how your embankment slope can be made. So if it is more sand than clay, you don't use a steep slope because there will be erosion taking place. So you'll use a more a shallow slope. But if it is high in clay content, you can use steeper slopes like 1 and 3. That means, well, it's vertical to horizontal. So therefore, the vertical to horizontal will be 3 to 1, where you can use steeper slope. But that is only if it's high in clay content. We don't go into that steepness. We recommend 1 to 2 or 1 to 3. In some cases, you can have as shallow as 1 vertical to 3 horizontal. And in those cases, those will be where you don't really have as much clay in the soil. Right, and we have the different base widths of the embankment. The top widths of the embankment are like 0.6 meter or 1 meter and 1.5 meter. And the base widths we have as wide as 4.5 meter to 8 or 13 meters. The heights of these embankments are usually like 1.3 meters straight to 2.1 meters in height. But basically, we recommend 1.3 meters in construction of ponds. Okay, so the side slopes, as I was describing earlier, the steeper slope are more easily eroded, and the slopes should be more gentle for soils that contain more sand. I explained all that, and as the slopes increase, erosion of the slopes increase as the size of the pond increases, because there are more waves in the water due to the winds which will cause waves in the water. So as the pond size is larger, the waves can cause erosion of the embankment slopes. The slope ratio of for example, 3 to 1, you have the volume of earthwork would increase, because that's in that case it will be a very deep pond, and the overall 3 to 1 in this case, meaning horizontal, 3 horizontal, 1 vertical, you will have more earthworks because of the fact it will be a larger diameter and it will be a larger area. So the earthwork in this case increases. The land area for the pond will also increase because of that slope, 3 horizontal, 1 vertical. A higher slope ratio makes easier when using bulldozers because it is less steep. So as I said, the 3 and 1 means it is shallow because it's 3 horizontal to 1 vertical. The embankment is shallow, so you're going to get a more shallow pond, and therefore the ease of access to the base of the pond using bulldozers to build the embankment. So the shallower the pond, you could use the bulldozer. The steeper the pond, you need the excavator for a longer reach. Right. This is what an embankment looks like. So you see the surface of the embankment, the top surface, and then the base is much wider. So that's the appearance of an embankment. Pond inlet structures, we usually recommend PVC pipe, 10 centimeters diameter, or you can have it 12, you can have it up to a foot in diameter. And you have also inlets done by shallow trenches that could also be used for inlets. And you can also have an inlet via a sluice gate, but we will not be considering this in this training, because in that case it will be for very large communal ponds. Sluice gates are used in those instances. Overflow pipe construction, we try to locate the overflow pipes at the corner of the pond, in this case, where it would exit into a channel that is built at the side, which will be an intermediate channel that connects to some outlet source like a river channel. So this overflow pipe, or in some instances, some people call it spillways, it is built through the embankment, and it is built at about 15 to 20 centimeters below the highest depth of the water level, the highest water level height in the pond. So as you see in this second diagram, this end of the outflow pipe is 15 to 20 centimeters below the surface level of the pond. It must be tilted at that angle, because when the pond is going to overflow, it will have to go through this pipe and exit at this end of the embankment, the outer embankment. The outer embankment has some gravel, stones, or boulders placed to prevent erosion of the embankment. So there are some boulders placed here so that when water exits the pipe, it would not erode the embankment, and it fills this small catchment here so that it can exit into another channel leading to the river or outsource. So this pipe is fixed in the upper part of the embankment as shown in the diagram, the pipe, and the pipe must be made long enough so that the overflowing end discharges the excess water beyond the toe of the embankment. So it must expel the water beyond the toe, which is the base of the embankment here, at this point at the bottom of the embankment. So it must be long enough to discharge water beyond that toe. Now, the overflow pipe is usually a 12 inches diameter. It can be secured actually with casing, cement casing, and the diagram of that would be this here, where you can build this casing around the pipe by pouring concrete around the pipe, and you will get a concrete bracket being formed that will prevent shifting of that pipe in the embankment. So this is built prior to the embankment being constructed. So you build this and have it in place, and then afterwards you fill the embankment in layers and compact. So the pipe would be angled slightly, and the protected concrete area is built around the pipe to secure the movement of the pipe. In this case now, this is another outlet pipe which is bent, curving down on the inside. And in this case, we use this type where it's bent downwards in aquaculture ponds where the fish are stored. So in order to prevent fish from going into the pipe is bent and is usually blocked at the end with a screen to prevent fish from entering the pipe. So this is only in the case of aquaculture ponds where fish are stored. These are the sizes of outlet pipes. We have for various pond sizes from less than 100 square meters right up to more than 5,000 square meters with various pipe diameters that are recommended. So these are important figures to take, we note when constructing the outlets for the ponds. The discharge capacity of the overflow pipes, we also take that into consideration. So for various diameter pipes, there's a discharge capacity. And this is important because when the Water Resource Agency has to inspect the pond in order to recommend water abstraction license, they need to determine the water discharge capacity. And in many cases, the discharge capacity for certain ponds may be 1,000 meters cube per hour. So 1,000 would be this one here, meaning say like 706, and the diameter of those outlet pipes would have to be 50 centimeters in diameter. So for large ponds, we have a 50 centimeter pipe, so that is like 4 feet, say you have a 4 feet diameter, but this will be in very large ponds in those instances where you have a discharge capacity of about 700 meters cube per hour. In those instances, we have larger size pumps being used to for water supply or for discharge of water. Right, module 7, we look at the theory behind the construction of the pond now, how we calculate it. We start off with the crop water requirement. This is the main aspect of pond construction, where we use an average daily water consumption of 2 to 3 millimeters per day for some crops such as watermelon, and for other crops like sweet pepper, we use 5.9 to 6.8 millimeters per day. So in this design calculation, I will be giving you the average figure of the daily water consumption, which we will use as 5 millimeters per day. So the crop water requirement design amount is 5 millimeters in this case, which I'll be showing you now. So the crop water requirement is dependent on these factors affecting evapotranspiration in crops, weather, crops, and management. So these are just some meteorological aspects of the crop water requirement, which we look into. All these affect crop water requirements. These are climate associated aspects. Major factors influencing crop water requirement or the crop needs for irrigation are sunshine, humidity, temperature, wind speed, type of crop, growth stage, and soil type. So as the previous slide showed, these are some weather aspects that affect crop water requirement. The volume of water required for crops, we have by the acreage where the rate 1 acre is 2/5 hectares or 0.4 hectares, and the various hectares, we see what are the water requirements per day. And if you use this table, this will be a very good guideline. For this 2-acre, the 2-acre plot, which is 0.8 hectares, so we will be looking at the 0.5 approximate hectarage, and we will be doing a calculation for 0.8, which is 2 acres. So 35 meter cubes per day is what the water requirement will be. So let us look at this calculation for 2-acre vegetable crop. So as I said, 0.8 hectares. Say, for example, tomatoes, a growing period of 100 days, 2 acres of land, and area of cultivation would be 6,400, because I will show you why it would not be the complete 2 acres. It will only, the area of cultivation it will use is 6,400 square meters, where I will show you the percentage of land that is used for that. The volume of water would be calculated as 6,400 by 5.005 or 5,000, which will give 32 meter cubes per day. So this is how the initial water requirement is calculated. This is how the setup is done, where you, in this case, a pond will be considered where this well exists. So this well can be considered as a pond, where you have a pump located on the edge of the pond, which will be carried, transmitting water via these pipes and valves and filters and so on. And from all the filters and valves, it is then carried to a main line, where there's an air valve connected to the main line. And this main line then is connected to a sub-main line across the crop, and the sub-main will then have the other sub-main, other laterals connected to the sub-main. And these laterals could be the polytube rubber hose, the polytube hoses. Those are the black hoses, and they are connected to the sub-main via these lines. So this is like the irrigation setup when you have the pond being built on the site and the connections to the irrigation system. Right, the volume of water required for livestock production. This similar to the crop production, I have values for the water requirements for livestock, and we have them for goats or sheep, cattle, and pigs. So these values are important before calculating the pond size, similar to the crop water requirements. The pond design standards for the 2-acre plot, as I said, we will be using the 5 millimeters per day and of water. 5 millimeters that will be the crop water requirement. Now the minimum water requirement at the source being 60 meter cubes per day. Irrigation water demand, I will show you how this figure is being calculated in the next slide. Okay, I will show you that right now. The 63.5, which is given as the irrigation requirement per day, we start off by the crop water requirement here, which is 5 millimeters per day, and we know the effective area to be irrigated is going to be 85% of the acreage of the land. So this is where I calculated 85% of the 0.8 hectares, and that came up to 6,475. So 85% of the total hectarage of 0.8 hectares which is equivalent to 8.8 by 10,000, which is 8,000. When you calculate 85% of 8,000 hectares, you get 6,475. Then the total crop requirement, we calculate as 5,000 of that figure, which is 32.4 meter cubes per day. So this is where the 32.4 in the table, which you saw, was the crop water requirement for vegetable crops. Next, we now look at how you determine the irrigation requirement now per day from the crop water requirement. We now calculate using a conveyance efficiency of 85%, where you convey the water via medium channel lengths, and so they are via the pipes or via surface water runoff. And the surface irrigation method being field application, we have an efficiency of 60%, and therefore the scheme irrigation efficiency would be 85 times 60 over 100, being 51%. So we incorporate a scheme irrigation efficiency because we have to cater for losses of water via transmission through the pipelines and through any form of application of irrigation water. So where we cater for any losses via frictional losses or leaks through the pipelines also, we increased the amount from 32 to a higher figure by 51%, meaning the efficiency, conveyance efficiency and application efficiency. So therefore, the higher irrigation requirement required is 32.4 divided by that efficiency, giving you 63.5 meter cubes per day. So we must cater for higher irrigation requirement to cater for any losses through the pipelines and so on. So that is how we calculate those efficiencies, the conveyance efficiency and the application efficiency, and we increase that crop water requirements by that efficiency, right? So for a 3-month crop of 100 days, we then multiply by 100 and we get a total irrigation requirement of 6,350 meter cubes per 100 days for the entire crop. So this 6,300 is the capacity of water required for the pond to be constructed. And so we know now what volume of water is needed for the pond. So now that we know how to work out the volume of water needed for the pond, we can also find out the volume of water needed for a 200-acre plot for pastures, because in many instances for livestock, we need to have ponds to be located in areas for pasture, which is also important for crop production. So as we worked out already, the 6,300 before, but let us look at how we are working out for the larger acreage. Well, we understand the above, which we did before, and now we can work out for 100 acres, we multiply the 63.5 to get 63,500 per 100 days. So now for a 200-acre plot, we therefore get 200. We actually use 100 because we worked out a 2-acre, and we multiply the 6,350 by 100 to get 635,000 meter cubes per 100 days. So if you go through the figures here, you will see eventually that we can work out also for pastures how much volume is required for a pond to be constructed for supply of water to pasture land. So let us look at pumps and then we will go to the break. This is the next area of calculation, pumps is done. This is the table, as I said, we use a 10-inch diameter because these were the gallons per minute recommended. Right, so we have the capacity of the pump and we also have approximate costings. So you can use these costings as guidelines. These are the various pump types. We mostly concentrate on the centrifugal pumps for these agriculture pumps. So there are two types of pumps, dynamic and positive displacement. We look at the dynamic pump, which is centrifugal, and there are axial flow pumps, mixed flow, and peripheral flows. So we concentrate mostly in agriculture on the centrifugal pumps. And these axial flow or centrifugal pumps can be either electrical or diesel driven. Mostly we recommend diesel driven as they're outdoor pumps and they are diesel driven. These are pump comparisons and we have pump display, these displacement pumps and dynamic pumps. And we have the comparison of flow rates, pressure, priming, flow types, and viscosity. It has no, the dynamic pumps, as I said, is what we recommend dynamic pumps in agriculture, and these are the strengths of the dynamic pumps. They go as high as 300,000 GPM, and the head varies with the flow rate, so you can adjust the height of the hoses to the various heights so that you can control the flow rates from the pump. As the flow rate changes with the head for the same revolutions per minute of the pump. Okay, water regulations and distribution of irrigation water. All right, so as calculated above, we have the effective storage dimensions, and we got 635,000 cubic meter. And we have minor channels with that storage. Those are the conveyance channels. And the water distribution, we have pipe networks for the water distribution. And for the distribution, we must have pumps which are required with a combination of gravity flow and pressurized flow. So we would have high flow rates, 6-inch pumps, 10-inch pumps, or 12-inch pumps. So basically, we use mostly these sizes, but for the small farmers, they could use up to the 2-inch, 4-inch pumps in some instances. Water regulation, we have manual valves, automatic shutoff valves, and all these are connected to the pump as I showed in the diagram with the irrigation system. And this is a diagram of a 24-inch hydraulically driven submersible axial flow pump. And these are for very large ponds, and they are for like the flows of like 15 to 20,000 gallons per minute per minute and so. Procedures. So this is the practical aspect of pond construction, how the ponds are built. Well, I saw any questions in the chat box about the material built of the Mr. Chedi asked about the embankment. I explained the material is in situ material, right? in one of the modules. On design construction procedure, right? So we have 5 basic steps. And remove the vegetative surface. Second, we demarcate by wooden pickets. Thirdly, you mark and cut the depth of the pickets so the operator can be guided accordingly. So you mark the pickets and to the depth of which it must be excavated. Excavate material to the depth by placing material around the perimeter to form an embankment. And you compact the embankment in layers of 150 millimeters thickness. So those are the heights of each layer. And you use a plate compactor to compact the side slopes, and excavator tracks is used for compacting the soil at the bed level and embankments. These are the pond construction process. You have the first one with the vegetation covering the land. Then you strip the vegetation in this second one. And then the third one, you start the excavation at various stages. This is just one of the stages of excavation. And the final one is you have the completely formed pond. This is just a design drawing of a top view of a pond that is constructed. We have also a diagram here of the fencing, which is recommended for protecting the perimeter of the pond so that no animals or any human may enter that area, because it's a health and safety provision. This is the process of pond construction. The process for new farm ponds, they must be constructed in accordance with specs, drawings, and dimensions on bills of quantities given by the engineer or the contractor, if it is the case of a private pond where the contractor builds the pond for the farmer. The critical dimensions are the proposed pond dimension, depth, side slopes, and spillway width or overflow diameter. The construction of the ponds are fixed price lump bid items, and the ponds are sited based on maximization of water collection from surface runoff so as to satisfy irrigation demands and minimize operational costs via pumping and cleaning of the ponds and interceptor channels directing water to the pond. The engineer must approve each pond in terms of siting, layout, and applicable design prior to commencement of construction. So in this case, we will have the officers from the county offices. They would be able to go and inspect these sites and determine the best layout and design prior to commencement. They will be able to do that after the training. This is the actual photos taken of the steps in pond construction. We have the first step, pond siting and land clearing. This is the first picture where you have the vegetation covering the site. The excavator will then come in and do removal of vegetation. This is an excavator in the background here. And this is an operator, one of the operators of the excavator. And this is the cleared site. And the cleared site, you'd see the raw soil material, the subgrade. This is the raw earthen soil here. So this is how it looks after site clearing. Then you have these slides taking out of the perimeter. You have the officers, the site officers here working out the area for the pond, the best location. It must be on flat land, not near to too near to the roadway or to channels. And they locate the best location, and then they start staking out with stakes. So these are the stakes here at the end, at the last picture. Following that, the excavator then comes and digs the trench of the perimeter of the pond. So this is the trench going right around the pond, and the excavator then removes all the soil from within that perimeter until it looks like this. And that same in situ material will then be used for constructing the embankment on the perimeter. So the side slopes are being dug accordingly to specs, and the base of the pond must also be excavated to the required depth and compacted as well, so that there will be less seepage of water when it is compacted. You get less infiltration taking place when the soil is properly compacted. And on the slopes, less erosion when the slopes are properly compacted. So from this stage, we see in some cases the excavator has to go to a deeper level. So the pond is actually done deeper with a next smaller area where there's a second smaller pond within the outer one. So in those cases, you will get a second slope being made, and there's that is where a deeper pond is required. So we try to keep the slopes constant, because if it is we had to go deeper, the slope would have had to been steeper. So therefore we had to do a smaller area of pond within the larger area, so that the slope will be consistent of 1 and 2, and it would not be a steep slope. So the smaller pond within the bigger pond was to be able to have more water storage by going deeper into the ground. Finally, after all the excavation and the compaction, we have the final pond, where these ponds are rain fed, and it fills up after about 3 to 4 days once there's rain. And we have in this case you see a pump at the edge of this pond, where the suction hose here, the suction hose is used to extract water from the pond and then to irrigate the crops in the surrounding areas. So we have the final completed ponds, rain-fed preferably, and those are the actual photos that were taken of ponds dug in the ministry. Right. So disposal of the excavated material, that is very important. The work consists of removing the piling of the topsoil, the excavation and disposal of material necessary for construction and rehabilitation of the farm pond, and grading of the site to required elevations. Where filling is required, this work will also include initial removal of unsuitable material, and this work includes excavation, grading of necessary channels or ditches, and in the construction of that pond. The excavated material becomes the property of the owner. It is the property of the owner and is disposed of by permission of the owner, or as directed as the engineer in the following ways. The excavated material could be the fill material, the fill surcharge, topsoil, waste to an approved dump, and other uses. This is what the excavated material can be used for. The excavated material, other than waste to the approved dump, shall not be removed from the site without permission in writing from the engineer, or as in the private land, in the cases of private land, from the owner. Soil type in the pond design construction, the soil type plays an important part in determining the ability to retain water. Soil is composed of organic and inorganic material, and it provides a medium for plant growth. It has various particle sizes like gravel, sand, silt, clay, and the percentage composition determines the suitability for pond construction, and the clay fraction is what is necessary to prevent infiltration loss. So these are some factors we can look into. Soil type determination, as I said, we determine the soil type from soil labs. So the soil lab does the testing, and the type of test done is a sedimentation analysis test. We mix the sample with distilled water and add a dispersing agent of sodium hexametaphosphate and shake it to allow it to settle. And the time recorded after 24 hours, we can then determine the percent of sand, silt, and clay. So the sedimentation analysis test done in a soil lab gives us the percentage of sand, silt, and clay, and we recommend 20% of clay. And the plasticity index would range from 12 to 24 for recommended ponds. Right, so that is the soil lab test. This is a map of Trinidad with the soil types. So from the areas, we can see from a map as well what type of soil exists. We can also look at this chart, which is a soil texture class, and we can determine from the sedimentation test of what percentage of sand, silt, and clay where the soil texture lies. So for instance, we want 20% clay. So therefore, if we have 20% clay, which is here, the recommended soil we would look if we get a sandy loam, or we try to get anything with at least 20% clay or more. They would be recommended for pond construction. But of course, these also, if we have these slopes, we can also look at those other types. The more the more gentle slopes would allow for a clay loam. Would allow for the sandy soft clay, because 3:1 meaning horizontal to vertical. So that will be a gentle slope. So it would not be a steep slope. This is how the soil test is done in the field. They do a borehole test. They take a sample from this, and they go in the field. They carry the sample back to the lab, and these are the samples after the 24 hours, where the sediments are allowed to settle after 24 hours. Rates are recommended for pond construction. Basically, the tractor, the D4 tractor. This is for clearing the land of all the vegetation, and so the D6 can be used as well for bulldozing. Then you have the backhoe, which I said it could also be used for the excavation and also for intermediate drains and so on. and then the roller compactor, which will compact the embankments, the dump truck for removing excavated material, and the grader for grading embankments and leveling, the excavator for digging the pond, and well, cranes are for extremely large ponds, which we don't use normally, but cranes can be used, and the hand compactor for the edges and sides of the pond. These are the sizes here. The bucket is a 0.5 cubic meter size, and the engine power and the weights are given. And this is what the medium-sized excavator looks like. And module 10, limitations of pond construction. This is some things that we observe over the years that happens when ponds are being dug. And it is, these are not recommended things in these limitations, so I'll go through it quickly. It is illegal to block existing dams or existing water channels with dams or blockages to store water, as this will prevent regions downstream from accessing water. It is advisable to build ponds. It is not advisable to build ponds in waterways along hillsides, as it is where runoff occurs and will cause erosion of the embankment. Ponds are not to be built on river reserves that falls within 15 meters of the riverbank. So we avoid going within 15 meters of the riverbank. And ponds are not to be built near roadways, that's not within 10 meters of the road edge, or utilities or houses or farm structures that could cause erosion of the roadsides and cause water to seep underground and damage the road and the foundation of buildings and structures. It is illegal to build ponds in valleys and depressions because these exist along water courses. And then it is illegal to fill ponds by abstraction of river water without obtaining the abstraction license from Water Resource Agency. Excavated material from the pond must remain on site, and unless permission is given for the removal, it must remain there. And if it is private land, the owner must give written approval, and if it is state lands, the engineer must give some written approval for any removal of the land. For module 11, we look at the abstraction application process, and the process for abstraction of water from rivers is by applying at water resource at the WASA, which is a branch of WASA. And the form LS1, that's one of the forms, must be completed, and a payment of $150 plus VAT for the administrative fee. The submission of a map of the site, a map of the site must be submitted, showing the proposed point of abstraction in the river channel. A completed survey and hydrological assessment is done by the regulatory licensing unit at WRA. And then a water quality analysis of the surface water is done as well. And the schematic diagram of the proposed structure for diverting the water from the river must be shown as well on a diagram submitted to WRA. The application to abstract water source would then be approved once all these conditions are met, and an index file is assigned to that farmer, and a license number is assigned as well. This is a sample of what they look like. The license shall remain in full force for 1 year from the date that it was approved till 1 year after. But in these cases, they normally end at the end of the calendar year for every license that is approved. So it will be for the number of months that the license was approved for. They will be charged a fee for how many months they have used the license for. The license fee is usually 10 cents per cubic meter, as I stated before, and the source shall mean the water source defined in Schedule 1. This is Schedule 1, and this describes what is the source of water. The source in this case is would be a river. Then the location, you will say whatever food crop project is the location of the source. Then the interest of the licensee is a lease, because you're asking for a lease for abstraction of water, and the purpose of abstraction is irrigation of crops. The means of abstraction, we look at a pump, which is the equipment to use, and the capacity, we will say 400 meter cubes per hour. And the method of measuring is the method of measuring the quantities abstracted was done by estimation by a field assessment. And the license rate per month is 20,000, for instance, approximately 20,000 meter cubes per month. So from this last figure, you will then calculate your fees at 10 cents per cubic meter. So that will work out to be approximately, in this instance, it would be per month 10 cents. You'll get $2,000 for the entire year. So if this rate is used per month, we use that figure, and that works out for the year that what you will be charged. Right, Module 12, we have the application process for pond construction program. So in the Ministry of Agriculture, the farmer will go to the county office and apply for the incentive. Then the application form would be filled out by the farmer, and the applicant information on the form includes his name, registration ID number, telephone contact, address of the farm, the size of the farm, the crop type, and the deed for the land. Then the guidelines for the required documents from farmers will be provided by the county officers. County office holds application form and schedules site visits by inspection of by the inspection officers at the county office. The inspection officers, together with the soil testing crew, visits the farmer's holding to ensure the criteria are met and the suitability of the land for the pond construction, including soil types and so on. The applicant is advised on a pond design from the inspecting officer, and visits would be made during the pond construction to monitor that it is dug according to specs. And finally, the last inspection and recommendation would be made for the incentive or subsidy approval. So the completed pond will be inspected by the officer from the county office to ensure it is suitable at a suitable location, that it is technically sound, that the embankments are stable, and that it was constructed according to technical specs. And it is ensured that the pond was built for the purpose which was intended. So from the start of the going to the county offices to apply, these are the steps till the end when the pond is constructed. The guidelines for qualification for the pond program, as I said, they must be registered. The farmer must be registered with the government. The topography, land preferably must be flat, and the farmer must have access to the centrifugal pond, as I stated earlier, a centrifugal pump, I said, and our diesel pump, but electric pumps, not normally, but sometimes we may come across. And the capacity is normally 3 to 8 horsepower. The farmer should be actively cultivating the land, and finally the farmer should have access to clean water sources. Module 13, we have recommendations for reduction of risk of contaminated water. Well, especially during the times of this COVID, we have to take special consideration of the quality of water, because there are risks with pathogens that may be in water, especially during the COVID times. So pathogens could be transferred to the land and crops by contaminated irrigation water, which represents a significant challenge to processors, producers, consumers, since it is established link between application of irrigation containing pathogens and increased frequency of the pathogen on the produce. And that leads to disease in humans and so on. So the examples of some of these pathogens in the irrigation water are like Salmonella, E. coli, rotavirus, norovirus, Cryptosporidium, Giardia, Clostridium, perfringens, and now we can even speculate that COVID-19 might be a pathogen that we might have to be careful about. Recommendations for reduction of risk, we have to consider providing guidance to the growers, for example, with risk assessments, monitoring, testing the water quality of the irrigation water. We can provide the educational material as well. So these are some recommendations we can have for water quality. We have 55 catchments in Trinidad, water catchments, and we have 55 catchments and 9 watersheds. So the colored areas will show you the 9 watersheds here. And in all 55 catchments in Trinidad, that is the reason for this is because in each of these 55 catchments, the water in the channels would flow to main channels, and because especially in the northern range, water flows through each of these catchments and through the tertiary and secondary channels to the main channels, which in this case here this would be the Caroni River. You get a lot of pollution of water in the Caroni River due to the effluent caused by pollution by industrial waste, municipal waste, agricultural waste, like pesticides and agrochemicals that pollute the water, and that is detrimental for food security, because it will cause disease and cancer and so on. So these catchments here cause water to reach the main channels and so on, and farmers are affected by the polluted areas in the higher regions of the catchments. In the higher regions, they are quarrying and so on, so you get sedimentation coming down to the lower regions and polluting the waters. These are some parameters of water quality, physical, chemical, biological, and radioactive. We look mostly at the physical parameters for pond construction. The chemical and biological, when we considering the water quality, where we try to avoid certain amounts of chemicals as shown here. We have restrictions for irrigation. These are the maximum and minimum values that are restricted for irrigation. We don't recommend water that has fecal coliform of values below 1,000. So anything has the fecal coliform that is more than these amounts, it must be 0 at all times. So these are other chemicals, nitrates, and these are the limitations for the chemicals. pH usually 6 to 8, dissolved oxygen dissolved solids, and we also look at, we see pesticides, we recommend less than or equal to 0.01 milligrams per liter, because anything more than that will be severely restricted for irrigation water. So the last column, any values in these equivalent to these are severely restricted for irrigation. We can recommend where there's no restriction or there's slight to moderate restriction. So we recommend values for sodium, for instance, less than 3 SAR for sodium. So salts, we don't recommend salt in the water for irrigation, as it causes salinity of the soil, which could destroy crops.
Michelle, we're not hearing you. You need to unmute your mic. You need to unmute your mic. Sorry, Michelle, we can't hear you. You need to unmute your mic.
Right, I think I'm now seeing, right. Okay, so this is the end of the presentation, and I thank you all for listening, and I hope it will be of use in future when you need to do any sort of pond construction for irrigation purposes and for flood alleviation. And I thank you, Mr. Jean, for allowing me this opportunity.
All right, thank you very much. Are there any questions in the chat? I didn't see any questions in the chat.
Okay.
If there are no questions, then we'd like to thank you, Michelle, for a very comprehensive presentation. And I would like to inform our participants that we're going to upload this as usual, and to inform you that the next session is going to be on November 4th on Integrated Demand Side Management by Neil Klassen of the Operators Without Borders. I'm Ignatius Shah, Executive Director at the Caribbean Water and Sewage Association, thanking all of you for your participation. And thank you again, Ms. Shah, for a good presentation.
Thank you, Mr. Jane, and I thank you to all the participants. Okay.
Yeah, have a good evening. Bye.
Have a good